Hello everyone, and welcome back. I'm Mr. David Carter. Today, I want to ask you a strange question. Can one object behave like both a solid ball and a wave at the same time? If your answer is no, then you're thinking exactly like most scientists did over 100 years ago. But today, you're about to discover why the quantum world completely changed that idea. By the end of today's lesson, you'll be able to answer these 4 questions with confidence. And don't worry, we'll use a simple English, easy examples, and clear illustrations. My goal isn't just for you to watch this lesson, it's for you to truly understand it. Before we continue, let's quickly review what we learned last time. On our previous lesson, we've discovered that everything around us, your body, your phone, water, even the air, is made of tiny atoms. And inside every atom, we found 3 important particles. So today, we're going to focus on one of them, the electron. You might be wondering, why are we talking about electrons instead of protons or neutrons? It's because electrons display some of the strangest behaviors ever discovered in science. They don't always behave the way everyday objects do. But before we can understand their strange behavior, we first need to answer a very simple question. What exactly is a particle? A particle is simply a tiny object that has a definite position. At any moment, you can point to where it is. It occupies one specific place at a time. Imagine you're holding a baseball. If you throw it across the field, you can watch it move from one place to another. At every moment during its journey, the baseball has a clear location. That's exactly how we think about particles. Now let's look at how particles move. When you throw a ball, it travels along a path from its starting point to its destination. If you recorded its motion with a camera, you'd see it following one continuous path. This predictable motion is what we expect from particles in our everyday world. So particles aren't just an idea from physics. Our everyday world is full of objects that behave like particles. A moving car, a flying airplane, a kicked football, all of them have a clear position and a predictable path. Classical physics describes these objects very well. Now we understand what a particle is. It has a definite position, and it moves along a definite path. But not everything in nature behaves this way. Some things don't travel like solid objects at all. So our next question is, what is a wave? Before we define a wave, let me ask you a question. Have you ever thrown a small stone into a calm pond? What happened next? You probably saw ripples spreading outward across the water. Those ripples are waves. Now let's look more closely. When the stone hits the water doesn't travel all the way across the pond. Instead, the disturbance moves outward. Waves are everywhere. The ripples on a lake are waves. The sound of my voice reaches your ears through sound waves. And sunlight travels to Earth as light waves. So waves are a common part of everyday life, even if we don't always notice them. Now let's compare what we've learned. A particle stays in one place at a time, but a wave spreads out as it travels. So particles and waves behave very differently. For many years, scientists believed that something had to be one or the other. What if I told you that an electron doesn't always choose just one? What if it can behave like a particle and like a wave? But when scientists performed careful experiments, they discovered something completely unexpected. Electrons didn't always behave like tiny balls. Sometimes they behaved like waves. And this was one of the biggest surprises in the history of science. Let's pause for a moment and review. So far, everything seems simple. A particle has a definite position, and a wave spreads out as it travels. These 2 ideas seem completely different. For many years, scientists believed that nothing could be both. Now, scientists became curious. They already knew electrons were tiny particles inside atoms, so they expected electrons to behave just like tiny balls. They believed electrons should always travel as particles. That seemed perfectly reasonable. Think about it this way. A football doesn't suddenly become a water wave, and water waves don't suddenly become footballs. So how could an electron show both kinds of behavior? Scientists were shocked because this had never been seen before. It challenged everything they thought they knew. So how did scientists discover that electrons can behave like waves? They didn't guess. They proved it with one of the most famous experiments in physics. It's called the Double-Slit Experiment. And by the end, you'll understand why it changed physics forever. For this experiment, we need only 3 things: a light source, a barrier with 2 tiny openings called slits, and a screen behind the barrier. The goal is simple. Let's see what happens when light passes through the 2 slits. Before performing the experiment, scientists made a prediction. They thought light would pass through the 2 openings and create 2 bright bands on the screen. That seemed like the most logical result. So everyone expected exactly 2 bright lines. But that's not what happened. Instead of only 2 bright bands, the screen showed many bright and dark bands. This pattern is called an interference pattern, and it was completely unexpected. Scientists had seen this pattern before. It appears when waves overlap and interact with each other. So when light produced the same pattern, it suggested something extraordinary. Light wasn't behaving only like tiny particles. It was behaving like a wave. So the double-slit experiment answered one question, but created an even bigger one. Is light a particle, or is it a wave? Scientists now had evidence that it behaved like a wave. But the biggest surprise was still waiting. What happened when they repeated the same experiment with electrons? We'll find out next. Scientists had already seen that light produced an interference pattern. But then, someone asked a bold question. What if we try the same experiment using electrons instead of light? Remember, electrons were believed to be particles, so everyone expected them to behave like tiny balls. Let's think about this. If you throw tiny balls toward two narrow openings, each ball must pass through one opening or the other. So if electrons are truly particles, we should see only two bright bands on the screen. That was the prediction. But when scientists performed the experiment, they couldn't believe what they saw. The electrons didn't produce just two bands. They produced the same interference pattern that waves produce. It looked as if each electron had behaved like a wave. Think about how surprising this is. Electrons were supposed to be particles, but the experiment showed wave-like behavior. So what are electrons, really? Are they particles? Are they waves? Or could they somehow be both? Now you might be thinking, maybe the electrons bumped into each other and created the pattern. That's a reasonable idea. So scientists tried something incredible. They sent just one electron at a time. If only one electron is traveling, can an interference pattern still appear? The answer shocked the scientific world. Let's find out in the next section. So far, we've seen that electrons created an interference pattern. But some scientists weren't convinced. They thought maybe the electrons were colliding with each other. So they designed a new experiment. This time, they fired only one electron at a time. Before looking at the results, let's make a prediction. If only one electron is traveling, it can't bump into another electron. So we would expect it to hit the screen as a single dot. And that's exactly what happened. Each electron arrived as one dot. But the experiment didn't stop after one electron. Scientists kept sending electrons, one, then another, and another. Slowly, something amazing appeared. Those individual dots began forming the same interference pattern seen before. This result amazed scientists. Each electron traveled alone. There were no other electrons nearby to interact with. Together, their impacts built a pattern that only waves were expected to produce. This was one of the strongest pieces of evidence that electrons have both particle-like and wave-like behavior. So what does all this mean? It means that electrons cannot be described as only particles or only waves. They show properties of both. This idea is called wave-particle duality. It's one of the fundamental principles of quantum physics. To summarize, wave-particle duality means quantum objects can display both wave-like and particle-like behavior. This depends on how they are observed or measured.